9 o'clock in the morning.
I'm grateful you're physically here.
Yeah,
she's online. Yeah.
Good morning, Megan.
Good morning.
Okay. Right. So, so good morning, everybody. Thank you for coming this early. I know it's unusual time for defense, so but we needed to put it this time to get the committee together. It's my pleasure to introduce our speaker today, Tristan Haseler. Tristan joined us in 2013, long time ago, and it's about 5 years. I think it's about the right time for a defense. And over the past 5 years, Tristan actually contributed several of our projects, hardware and software, actually, from cosmic detectors, maintenance and monitoring, to actually helping with building the modular rate detector. And actually, at one point, he actually was managing our small cluster, computing cluster. But actually, what distinguished him, actually, in my opinion, is actually his willingness to help the students, especially new students. And acknowledgement for his hard work, and he won this year the Outstanding Advanced Graduate Student Award. But his hard work and dedication was not limited to his research, and that should be actually an example for all our students, but also teaching. So I think in 2016, he actually won the Outstanding Graduate Assistant Teaching Award. And so, but over the last couple of years, his focus shifted towards his thesis project, which revolves around bottom-up part production. And that's what we will tell us about today. And so, Tristan, you have the floor.
All right. Well, thank you for the kind introduction. Thank you, everybody, for being here. Again, I'll be talking about B-quark production in proton-proton collisions at 510 GeV. Here's just the brief outline of my talk that I'll be following today. So we start with the standard model as the background to this story. The standard model is built upon decades worth of experimental research. It was finally pieced together in the 1970s or so, and it is used to describe the elementary particles and the forces between them. So we have here the table of the standard model. I'll start with the fermions on the left, where we have the 6 quarks and 6 leptons. These can further be broken down into 3 generations. There's, of course, the gauge bosons on the right, which are the force-carrying particles mediating the forces between these. And there's finally the Higgs boson, which was theorized several decades ago and awarded a Nobel Prize for just that, and was experimentally verified only a few years ago. Within the standard model, there are several theories that describe these interactions, them being, they are QCD, QED, and the weak force. So quantum chromodynamics is going to be the highlight of today's talk. It is describes the interaction between quarks and gluons. Of course, the gluon being the force carrying particle in this case. Electrodynamics, the force carried by the photon, and it is the interaction between electrically charged particles. And the weak force is carried by the W and Z bosons and is responsible for the flavor changing decays of the quarks. I say flavor, that is in reference to the type of quark in question. So there are 6 flavors in this case. These particles make up composite particles. I have just some quick examples here. Are the baryons. These are 3 quark particles that involve, of course, also involve gluons to bind them together, the proton and the neutron. And these are considered ordinary or everyday nuclear matter. And these are composed of first-generation particles. Next up are mesons. These are 2 quark, or I should say quark-anti-quark pair particles, again, with some gluons binding them together. Just 2 examples shown below. So these diagrams, although colorful and beautiful, actually represent something a little further, is the color charge carried by the quarks and the gluons that is involved in the strong force. So these composite particles are more than just the valence quarks. These are the quarks that define the properties of the particles. As you add energy into the system, we start seeing things known as C quarks. These are quark-anti-quark pairs that kind of pop in and out of existence within these composite particles. So the motivation today, this is why I'm here, this is what I'm interested in, is the QGP, or the quark-gluon plasma. And what exactly is that? It's this state of matter that's thought to exist microseconds after the Big Bang. So I have here this diagram of the history of the universe. We have modern day over here on the right, the Big Bang over here on the left, and the QGP is found in this region here. You can see this axis is time, temperature, and energy. Of course, time increases, temperature and energy decrease as the system expands. And we're able to probe these this region with modern day experiments, such as those found at the LHC and RIC. So the QGP itself is a hot, dense, and strongly interacting medium made up of free quarks and gluons, and that is very important, as I will get to momentarily. But very quick information about the QGP, just some highlights of it, is that it has a very short lifetime, at least when produced in a laboratory at 7 femtometers C, a temperature on the order of 10 to the 12 Kelvin. To give you an idea of how hot that is, I have the temperature of the sun noted here in the millions of Kelvin. And then the energy per particle is on the order of 170 to... It's a very short period of time. Fair enough. I cannot relate it to attoseconds now. I'm not unable to do so. Yes. Well, certainly. Oh, it's definitely, yeah. It was certainly. So, well, that, yes. Yeah. Okay. Sure. So then the energy per particle is 170 to 175 MeV per particle. To give you an idea of what that is, they say the kinetic energy of a mosquito is on the order of 1 TeV. So that is relatively small, but of course the mass differences are huge here. So the QGP falls on the QCD phase diagram, which is shown here on the right. This is very similar to the phase diagram of water, or conceptually similar, in the sense that water has liquid, gas, and solid as ice, right? So this is nuclear matter, shown here with temperature and baryon density on this x-axis. QCD is at high temperatures across several, much of the baryon density range. And if you go to low temperature, low baryon density, we find hadrons, or what's called the hadron gas. And this is just, again, normal nuclear matter. There's a phase transition between these, which is shown here. And again, highlighting the regions of where we're able to probe with modern day experiments. So QCD has two distinct properties. They are color confinement, and that is that we find no single quarks in nature. Hence the reason we have these composite particles, as well as asymptotic freedom, which is the idea is that as the energy scale increases and quarks move closer together, that they are weakly interacting. But of course, I can talk about the QGP in this grand scheme of things, but we need to be able to quantify it to further understand it. And we can do that in several different ways with observables or probes, at least in the laboratory setting. I'll go through these quickly. We have particle flow. This studies the bulk properties. It helps us understand the medium and how it expands and evolves over time. We have something called particle jets, which are high momentum particles in collimated beams, and they're used to study the energy loss through the system. There's something called quarkonia particles, which are quark-anti-quark pairs of the same flavor. And if you know the binding energy of these particles, you can determine the medium temperature. There's also low mass vector mesons. Here's just some examples of them, the rho, omega, and phi. And these reflect the initial evolution of the system through their soft processes. And finally, there's open heavy flavor, which is what I'm going to be highlighting today. This is a meson made up of a heavy quark, which I will describe momentarily. And this is used to determine medium density, which I'll also discuss. So heavy flavor quarks are the charm top and bottom. Their mass is what defines them as heavy flavor at greater than 1 GeV. That's generally in reference to the proton, which is on the order is about 938 MeV. So it's certainly larger than that. And their production can directly test perturbative QCD. So to give you an idea of their relative sizes to one another, as well as to the proton, which is this gray circle down below, circle at the top, the lower green one is the bottom, and the charm is up here on the top right. This is this is not this is just this just represents their masses in some area. That's all this is. And so the highlight of today is going to be the bottom quark and its production, of course. Its mass is on about 4.2 GeV, and I'll be talking about its decay semi-leptonically, or at least their the final measured particles would be through the muon signal, which I'll describe. So moving on to the theory a little bit. So again, we're studying the QGP, but first we have to make it. We're not able to study it, obviously, from 13.8 billion years ago. So we have to recreate it in the laboratory, and we do so by colliding and smashing together heavy ions. So this is just a quick simulation picture of a gold-gold collision, all the particles that we produce in the process, and them entering and interacting with the detectors. A little bit more about how we produce it. We use, so these are relativistic heavy ion collisions. So we're smashing them together again and looking at what comes out. The more energy you add to the system, the more degrees of freedom you will end up having. I use AA here to represent the collision species. And this picture here to represent the collision or the beginning of the collision. So we bring these ions up to relativistic speeds. So at 99.995% C. So as that happens, these begin to Lorentz contract in the reference frame of the laboratory. So that's why they are flat here in this pancake shape. And then they begin to interact in the hard scattering processes. We start separating out the quarks and gluons and forming the QCD medium, the QGP medium, I'm sorry. They eventually, so the QGP evolves a little bit over time. It interacts, it expands and cools down. And as I mentioned, because of color confinement, the quarks begin to hadronize, forming composite particles. These composite particles don't tend to be stable. Again, we get this cooling effect of the medium, and the hadrons begin to decay into stable or semi-stable particles in this freeze-out phase. And it's at this freeze-out phase is where we're getting the particles that we're able to actually detect. So we have to look at these detected particles and take the information we know about what we're colliding and at what energies, and we have to figure out this whole process. Again, I mentioned heavy flavor as the interest of this talk. So I want to talk a little bit more specifically about that within the QGP. So I have this diagram shown here on the right-hand side. This is with phase space on this axis and time shown here. We have the incoming beams, and we produce a BB bar pair. They can transverse the medium, they eventually hadronize, and eventually go to the freeze-out stage and decay into the measurable particles. So they're produced early in the collision process, and this is due to their masses being much larger than the lambda QCD, which is about 200 MeV. They're good probes because they can transverse the medium, they can travel through it, and they interact with it via scattering, leading to energy loss, which is how we determine the can help determine the density of the medium. And this makes them a good internal probe. This is this fragmentation of the particles. And the decay, not fragment, sorry. So they hadronize, and this is their final decay products. I think you're correct. Maybe the bar should be a bit shorter, but I think with Yeah, I think that's just the text. I'm sorry, but of course it's not that simple. Up to this point, I've been talking entirely about heavy ion collisions and making the medium, which is of course what we want to study as nuclear physicists. We want to study this extreme temperature and density medium, but there are underlying processes we need to understand. So we want to understand what we call cold nuclear matter effects, considering if you call the QGP the hot nuclear matter effects. And this is just due to the presence of normal nuclear matter. We typically study this in small or asymmetric collisions where we believe the medium is not formed. But we need to further understand the simplest of all cases, and that is proton-proton collisions. Again, we definitely know there's no QGP formed here, and we can start looking at production. So I've talked about it kind of slightly backwards because you actually have to start with PP and work your way up. But again, the ultimate goal is studying the QGP. So the goal of my work is the study of quark production, specifically the B quark production. And we do so by looking at the production cross-section as well as the opening angles of these quarks. So the production cross-section is just a fancy way of saying how many pairs do we make per given collisions. And the opening angle gives us some insight into the actual mechanisms at play. And so the motivation here is that production is generally poorly understood. Specifically at RHIC energies, it's been found that previous measurements tend to be a bit larger than perturbative QCD calculations. So we're trying to understand that. And so we need this baseline measurement, of course, to understand it within the QGP. So that is why PP collisions are so important, is because they serve as this baseline measurement. So again, this is the specific goal of this work. So talking a little bit about the production mechanisms themselves, these are the three dominant mechanisms. Within perturbative QCD, the flavor creation is a leading order process, while the flavor excitation and gluon splitting are considered next to leading order processes in the expansion. So flavor creation is where the two quarks produced are involved in the initial hard scattering process. So they tend to have large symmetric momentums in back-to-back production. Flavor excitation, as I said, is next to leading order. In this case, one of the quarks participates in the hard scattering process. So one shoots off and the other one kind of meanders a little bit. So you get some intermediate angle and asymmetric momentums. And finally, in gluon splitting, you get small angular production and small asymmetric momentums between the quark pairs. I mentioned this study is done through muons. It is specifically done through dimuon pairs. And we have developed a novel technique to separate out a dimuon signal without having to worry about secondary vertex information, which requires fancy, expensive detectors, as well as huge amounts of analysis work to look into specific kinematics. We use like sign pairs because it removes complications from the unlike sign sources. Muons have a relatively large branching ratio, around 10 to 11%, from B mesons down to the muon, which is quite nice. It is a very clean process relative to other such studies. But of course, how do we measure these muons? That is what's coming up next. I'll talk about the experiment a bit itself. So work was done at RHIC, the Relativistic Heavy Ion Collider. It's an extremely versatile machine. It's located at Brookhaven National Lab on Long Island. So up until recently, I had several experiments. It is now down to STAR. Phoenix and STAR ran in parallel for many years. Phoenix being the experiment that I'll discuss today. This complex also includes the AGS, which has 3 Nobel Prize awards to its name as well. So here's a picture of the nuclear physics group in the counting house of Phoenix. This is from March of 2013. So being part of a large collaboration, you have to put in your time and effort, which is fantastic, and we're certainly so happy to do so. So as I mentioned, RHIC is versatile. Hopefully I can explain that here. So this diagram has center of mass energies along this axis, the x-axis. It has collision species on the y-axis, and some average luminosity values on the z-axis. This just represents average amount of beam time, typically about 8 hours at RIC, in my experience. So RIC is the bread and butter of their program is through the goal-goal collisions across a wide array of these center mass energies, as well as colliding at 200 GeV, almost all of these species. Another feature shown here is the D-Gold program at RIC, and this is used to, in this beam energy scan, and they're trying to determine this phase space transition that I showed on the QCD diagram there. So this work, again, is proton-proton collisions at 510 GeV, which I've highlighted there. And that data set was collected in 2013. So the detectors used are from the pioneering high-energy nuclear interaction experiment, also known as Phoenix. I have here just a schematic of all the detectors and subsystems. They're broken down into 4 arms, if you will, 2 magnet systems as well. So there's what we call the central arm, so the central magnet, which is kind of better seen on the right-hand side here. We have the muon arms, south and north as they're called, as well as the muon magnets. But Phoenix is more than just a big chunk of metal. Over at least the 16 years of runtime, plus the before and after, there's been hundreds of people involved. We're talking almost 200 papers, 200 theses, students, postdocs, undergrads, engineers, etc. So lots of manpower going on here. We are an international collaboration, which I am happy to say I'm a part of, which brings in lots of different points of views and keeps things very interesting. I do actually have to talk a little bit about the experiment, though. So moving on, so I'm going to focus on the muon arms because this is what is used to measure, make the measurement. So the muon arms consist of the muon tracker and the MuID, the muon magnets, and they can measure muons within these kinematic regions. So we give you an example of how the collision works. Within the detectors, so the proton beams come in, ideally they collide at the center of the system, and whatever is happening in those processes come out, and we measure our muons. So the muon tracker is this inner detector here. It's 3 layers of cathode strip chambers, which are highlighted in the green here. This also actually includes the muon magnets, which are the lampshade shape objects surrounding the muon tracker. This produces a radial magnetic field so that as the muons travel through these cathode strip chambers, ionizing the gas, their curvature, the path is bent, the trajectory, and therefore we can determine the particle's momentum. Next up is the muon identification, or the MuID as we call it. It is used to do exactly as its name implies, to determine their muon particles. It consists of 5 layers of alternating Oroki tubes and steel plates. So these are basically single wall drift chambers. They're stacked into arrays with X and Y. And then there's several layers of those. And that is how we can get our hit information, and as well as make sure that we look at the particles coming out the very back and look at the muon candidate particles. Again, here's a picture of myself in front of the north arm muon tracker. This was taken in 2015, maybe. Just to give you an idea of, of course, the relative size. The muon ID is 10 meters tall, and this is just a central arm on the left-hand side. I'll briefly just mention some kinematic variables that are used throughout the rest of this talk. So there's the invariant mass. This is a 2-particle study. So ideally, we're measuring muons, muon candidates, and determine their invariant mass. We look at transverse momentum, which is the momentum in the XY plane. This is done for both single particles and dimuons, or 2-particle systems. Of course, this is the plane perpendicular to the beam axis. There's also rapidity, which is this y here, and this just references the projection of the particles in reference to the z axis. So moving on to the bulk of, onto the work itself. So the signal here is dimuon like sign pairs, and I'll just briefly talk about how we can actually get those. On the left-hand side, we have what we call the B decay chain, and on the right-hand side, neutral B meson oscillation. Starting with the decay chain, if you produce a BB bar pair in a collision, again, they hadronize, and you can have them decay semi-leptonically, about, again, 10 to 11% of the time. But a B meson can further decay into a charmed meson, or a D meson as they're denoted here. And that happens quite frequently at 90% of the time, and that can further decay semi-leptonically. So we're left in this process with these 3 muons, and we can pair them up, and we get both like and unlike sign pairs. On the right-hand side, we have the neutral B meson oscillation, again, producing pairs in the collision process. A neutral B meson can consist of a B quark and either a D or a strange flavored quark. And so the particle can oscillate, and we can get this nice, clean, like sign pair from this process. Just to give you an idea how nice the like sign signal is, for an analysis, I have this table here of all sources of muon pairs, with unlike sign on the left, like sign pairs on the right, and further separated by mass windows, separated at 4 GeV. So in the unlike sign pairs in both masses, you see we get some quarkonia pairs. We get both open bottom and open charm contributions. We get something called the Drell-Yan pairs. But as soon as you step away from unlike sign pairs and look at the like sign pairs, we're left with mostly just open bottom pairs. There are some charm, open charm pairs in the low mass region, but they generally are negligible. And we actually end up using this mass region for a different purpose later on in the analysis. So we focus on the high mass region, ideally looking towards these neutral B mesons that oscillate. Of course, there's hadronic background in all possible scenarios, so that also needs to be addressed. So I talk about making dimuon pairs, but I will get a little bit more into what that actually means. So we collect the muon particles, of course. We run the experiment. We collect them in the detector, and we therefore have our muons. And then we blindly pair them in what we call same event and mixed event pairs. And this figure here is a little misleading because when we measure muons, we actually don't know their sources. We know nothing about them. We just know that we have these muons, right? So as I said, we can pair them up. You could potentially pair them up and get the actual signal that you want. If you have some hadrons here, and if they're from the same subprocess and you pair up their muons, and those would be considered correlated hadronic background pairs. But you also end up, because we're pairing them combinatorially, we end up just kind of randomly pairing them up in processes that have no physical meaning as well. So when you pair them up randomly like this, you can determine the invariant mass distributions, which I've shown here. So this contains all those contributions, and we have to further separate this into them. Thankfully, we are able to do so. I will next talk about, so the first contribution we address are these accidental pairs, which are the non-physical pairs. And we do so by using event mixing, as I mentioned. So if you look at two neighboring events, assuming they have similar kinematic properties, such as collision vertex, position, and so on, we can pair them up. And because they're from two totally different events, we know that when you pair them up, there's no physical meaning to them. Of course, they have their kinematic properties, and we use those. So we pair up whatever it may be. And of course, when you're pairing up from different events, you have you get much more, many more counts and statistics over from what we call the same event pairs. So now we overlay the mixed event pairs on our same event pairs shown here. And of course, we get more counts in general. And we know that the low mass is dominated by accidental pairs. Our signal is dominant in this higher mass region from 4 GeV onwards. So we have to be able to normalize this so that we can subtract out this contribution to our distribution. So we've developed a novel technique to do so. It is a multi-step process, and I will try to keep it as simple as possible. So the first step is to, so ideally here we're normalizing this is the ultimate goal here. And so we know the low mass region is mostly background, but we don't entirely know whereabouts in the regions they are. So we use different normalization windows, and we take an average between them. So the normalization factors are just the counts in each of the distributions divided by one another. And of course, as I said, we use an average. So then we normalize our background, this accidental background, and we subtract it from our foreground, and we're left with physical pairs. And so the first step looks something like this. So again, we get our correlated signal, but we see that there's a little bit of over subtraction in the low mass region, and we know we can do better. So we incorporate an open bottom signal from simulation, which has some inputs from data. So we are confident in this the shape of this distribution. We then incorporate it into our normalization factor determination. And we do that many, many times iteratively. Of course, we repeat the process, and we end up with this distribution shown down here. So this is the same event pairs again in the black points that hasn't changed. We normalized our foreground, our mixed event background, and we get our correlated pairs. And we also see that in this process, we actually normalize this simulation input to the high mass region where we expect our signal to be, because this is our eventually is our signal. So this method stabilizes around iteration 4 or so. It approaches some normalization factor. And so we actually use this normalization factor to normalize our mixed event pairs and our delta phi distributions. These are the opening angles of the muon pairs. And we see that at 90 degrees, where we expect no signal whatsoever, that there's a good match between the like sign and the mixed event pairs. So the accidental background has been now taken care of. We know what that contribution is. And we have subtracted it out. There is actually a missing step, which I will briefly discuss now before moving on to the next background. So all of the plots I have shown have involved some other work, underlying work. And this I want to highlight because this is many weeks and months worth of work. So when we look at our muon particle candidates, we actually applied data quality cuts to help reduce hadronic background, as well as any anomalies in the data. And we do so using the J-psi meson, actually, because it is a resonance particle, it's easy to work with, and its mass at 3.1 GeV is relatively close to our high mass region. And then we also apply some acceptance and efficiency corrections to our distributions. Those are determined here through an embedding simulation, which is where we put in background noise from data into our simulation, and we can correct our distributions. So we apply these corrections in mass and delta phi to our invariant mass and delta phi distributions. Okay, so moving on, again, are the hadronic contributions, which are now part of this correlated distribution here. And we do this in a two-step process. So the first step is determining hadronic single particle survival probability. We want to know how often we can get pion or kaon to the back of the detector. This is done through a Pythia physics simulation, and it's fed into a geometry and tracking simulation, which helps mimic the detector effects on these particles. And so we know that particles, obviously, they travel into these detectors, but as I mentioned, this mu ID is actually it's actually built to prevent this from happening, right? But we know it does happen. So we do get some hadrons out in the back. We also get some that decay within the system and produce the muons, of course, that can also be misidentified. So we determine the survival probability. And then we use it to produce, again, in simulation, dihadron pairs that represent correlated pairs. And we weight them by this probability in PT. So the simulation output, or the I have here compared to some data. This is a differential cross section in PT. The data is from the UA1 experiment from many years back. It actually was measured at 500 GeV, and the Pythia, of course, is run at 510 GeV. While we don't expect many differences between 500, 510, so we go ahead and take a look at it. So we see that in the low PT region, there's some general agreement, and we're happy with this. But as you go down to go towards the higher PT region, you see it starts diverging a little bit. But we argue that the order of magnitude here difference is large, as well as the fact our signal to background ratio of the hadronic pairs to our open bottom is also very small. So the effect is minimal. So here's the single hadron survival probability distribution. This is versus PT. This is a ratio of all the particles that do make it out to the back of the detector in the simulation to all of those that are fed into it. So you see, obviously, the higher PT, higher energy particles are the ones that are going to mostly make it through. We then fit it to a third order polynomial with this confidence band of 95%. And we use this fit to help remove statistical fluctuations. So then we sample the fit and we apply it to the individual hadrons that we pair up, and we get our dihadron distribution. This jumps ahead a step or so, but we are now looking at, instead of looking at yields, which we've been looking at in the past, we're now looking at differential cross sections in dy dm. So here I have the like sign pairs, the correlated like sign pairs as a cross section, as well as the hadronic contribution shown as these two lines here. This is a two-arm analysis, but we actually, so all the plots I've been showing are for the north arm, but we do the same again in the south arm. And because they're corrected, acceptance and efficiency corrected, we can take an average of them and to help reduce the fluctuations. So we have our differential cross section and the like sign pairs, and we need to get to a total cross section. And we do so in several steps. The first one being is applying this alpha parameter here, which is shown plotted against mass. And this is the ratio of like sign dimuon pairs from the oscillation process divided by all like sign pairs from open bottom. So this also includes the decay chain process. And you see as you go to higher mass, you get larger contributions from the oscillating pairs. So we multiply this by the differential cross section that I previously showed, and we get pairs from oscillation. We then apply this beta factor, which is again shown here versus mass. It is actually mass independent, but it is the ratio of like sign pairs from neutral B meson oscillation again, but this time it is divided by all dimuon pairs from open bottom. Right, so we're scaling up from like sign pairs to all sign pairs. We also did an extensive systematic study. This is, again, months worth of work. This table does it no justice with our systematic sources. I highlight the scale model dependence down here, partially because this is the final piece to from our measured cross section, which is measured to be about 1% within the Phoenix detectors, to 100%, right? So it is something we have to carefully take into account. So we look at our open bottom differential cross section now. This has the alpha and beta parameters applied to it, and this is the cross section for all open bottom dimuon pairs. The systematics applied, all backgrounds, of course, accounted for. So if you integrate this over mass, you're left with d sigma dy of 0.37 in nanobarns. And there's two more pieces to get us to a total cross-section from this differential cross-section. The first being the branching ratio, which is at 10 to 11%. It is well known, well understood value measured by the PDG groups, or put together by the PDG groups. And this represents the idea that because we're measuring only through one of the decay processes, while B mesons actually have many decay processes, we need to account for that. It's also squared because it's a two-particle study. And then finally, we apply this scale factor. which is coming up right here. So this is how we determine the scale factor. This is B parent rapidity. So what the scale factor does is, again, it scales our measurement up to full phase space because we're not able to measure it. So this is determined through multiple models with several different input parameters. The large distribution on top is full 4 pi space of B parent rapidities that produced the dimuon pairs. And then we, of course, the analysis is done within the muon arms in this high mass region. So once you account for that, you're left with these distributions. You take the ratio between them, we get our scale factor, and we can determine our total cross section. So here's the total cross section itself. It is this point here, which we add to this plot. So this plot is total bottom cross section versus center of mass energies. This green line and its associated uncertainties are next to leading order perturbative QCD calculations, and there's also alongside the line other measurements done by other experiments over the years. So we have added this point here. We have found a total cross section of 14.9 with associated uncertainties and microbarns, and so at the calculation at 500 GeV again is 11.2. So it is slightly larger, of course, but it within the uncertainties, it is okay. If you look at the ratio here, this is the ratio of all the points to the calculation. And generally, as I've mentioned in the past, we see that at RIC energies, that which is this central region, we see that we're slightly above. So it's trying to contribute to that understanding. So moving on to my summary, I've talked about and studied open heavy flavor and its production, and I've done so in proton-proton collisions to serve as a baseline to QGP studies. Again, in proton-proton collisions, there's no QGP and there's no nuclear effects at that point. We have done so through the neutral B meson oscillation properties, which provides us this clean light sign signal in the high mass region. And finally, we have measured the total bottom cross section and is consistent with perturbative QCD calculations within the uncertainties. I would like to acknowledge and thank everybody who's helped me along the way, of course. Thank you, committee members, for being present and being here and reading the thesis. Thank you to my advisors for putting up with me for so long. Of course, thanks to the Phoenix collaboration. They've been very helpful with the analysis, and all past and present members of the Georgia State Nuclear Physics Group. And thank you for being here.
Thank you very much. I think the way it goes, we open the session for general audience, and we hold committee members for data. So, any questions from the audience? Any questions? Any takers?
Yeah, sorry, square root S. What is the S?
It's a Mandelstam variable. I don't know too much about that. It's just the center of mass. Yeah, it represents the center of mass collision energy.
Wouldn't that be a more sensible symbol?
Yes. Yes, certainly.
Any more questions?
You guys not drinking enough coffee?
Can you guys no questions?
Yeah, well, I've been up all morning.
Okay.
Actually, I just touched on this briefly. I was wondering if you could expand on more detail. Why did you choose this particular production method of study? Why particularly?
Well, we're studying all production mechanisms. So once they're produced, so we're actually studying them after they're produced, right? They hadronize. And we're just picking specific hadron signals to study them. But the full production, we want all of them.
But he's asking, for example, I think maybe why you're studying the like sign from the oscillation, which is.
I mentioned you said it was just a good way of getting a good signal. I was just wondering how it compared to other methods out there for studying the same.
So another method, as I very briefly mentioned, to study heavy flavor, open heavy flavor is through secondary vertex information. And again, I mentioned that we use expensive detectors in the analysis itself. So in that case, we're using silicon-based detectors that get very high resolution hit information of the muons, and is used to determine the decay length of the B mesons to the muons. And that is, while a good method, is very time consuming and complicated.
To make it simpler, you know, the alternatives, either you look at this, the muons that they have the same sign, or the muons that have different sign. The one they have same sign, there are a lot of other resonances that hits the stick out and screws up your work. That's as simple as that. This
the
weakness is that you don't have the J psi, the psi prime, you don't have higher resonances and all these, and especially some of this one, which we call trillion, that really go to this one.
So there's only, so in all cases, right, we still have the mixed event pairs, the accidental pairs, are in all cases as well, hadronic backgrounds in all cases, right? And that's all we removed here. And as Dr. Dastur is saying, once you start looking at this, you have to separate all the contributions individually and look at their relative yields.
The problem with that method, the unlike sign, is that mostly we don't know the exact contribution to the total spectra. And so we have to use a lot of theory. And our collaborators, for example, from Stony Brook did it, and you can see there's a lot of theory. And that's the theory people. But there's always some doubt.
We don't put it to error bars, you do. That's my case.
So that is clear. All right. Any more questions? It's much more fun than
It's a lot of fun. You guys are missing out.
Okay, so if the audience are done, so thank you very much for coming, especially early on.
Yes, thank you.
I'll ask you guys,
Please say coffee and donuts.
take coffee and donuts.
I'm going to do myself.
Maybe a few minutes.
Still there, Dr. Connors?
And also the camera and that business.
I'm still here.
Okay, we're going to take a 2-minute